So just, this is, and again, this is going to be a lot for this section here, expressing concentrations using mole fractions, molality, which we were introduced to in the lab, describing some of these solute concentrations, whether it be with vapor pressure, boiling point, freezing point, osmotic pressure, and performing calculations, understanding distillation applications here. So, properties of a solution. Right? So properties of a solution. So there's different properties for the solute, different properties for the solvent. Right? And the properties depend on not so much the temperature, but the acidity, the basicity, the density of these, right? And that's what we're going to take a look at for what we consider to be colligative properties, and then we'll be able to maybe just identify and understand better just what that term colligative properties actually is, right? So colligative properties, we're going to cover vapor pressure lowering, right? How do we lower the vapor pressure of a certain substance, right? Understand boiling point elevation, right? When we put some solute into the solvent, how does that affect the boiling point? How does that affect the freezing point? We had a little experience with the lab that we did yesterday, and then understanding what we consider to be osmotic pressure. So when we're looking at molarity, we all know what molarity is, right? We've dealt with molarity for a while. Is this capital M is molarity, which is equal to what units? Moles over liters, right? So that's our molarity. We've dealt with mass percent. We've done calculations with that, trying to determine empirical formulas and whatnot, molecular formulas using mass percent. And then we get our mole fraction. We learned mole fraction as this X here, and we used it with partial pressures, right? Trying to understand this mole fraction, right? So the mole fraction is we need some moles. I'm going to put the moles of, let's use I here. So the moles of I, if I want the mole fraction for I, we're going to take the number of moles of I over the total number of moles, and then we get what we consider our mole fraction. And then we have now this small m here, right? This lowercase m, and this is equal to something we call molality. You might even see the term, read the term molal, right? Sometimes we use molar here, right? The molar concentration, right? So here there's also, we can shorten this up and we'll call it the molal concentration, but molality is equal to moles of solute over kilograms of the solvent, right? This is moles per liter of solution, right? Moles per liter of solution, and this is just the kilograms of the solvent. So in a solution, right, we can have solute and solvent. So if we're ever asked, is we need to actually, we're going to come up with methods in order to segregate that and just get the mass of some solvent. Right? So molality. So we're going to take a look at some problems here and just do some conversions, right? Some dimensional analysis in order to understand what we're looking at for molality. So we're just going to work through these 5 problems here. So what is the mole fraction? What is our mole fraction? And what is the molality? So 2 things we're going to determine. They contain 850 grams of ammonia. Or 0.850 grams of ammonia. The solution contains 8.50 grams of ammonia, and it's dissolved in 125 grams of water. So here, we could get the mass of the solution, right? The mass of the solution is we would simply just add all those up. But because if we're looking at this, which one of these would we consider just to be the solute? What was that? The ammonia. Why would we pick ammonia? Because it's smaller, right? So the whatever's then smaller is going to be our solute, and this would be our solvent. So as far as, oh, actually, let's not move there. Let's go ahead and get the mole fraction here. So we're going to go and convert both of these into moles. This is 14.01, this is 1.01, there's 3 of them. So let's go with 17.04 grams of ammonia for every mole of ammonia, and this is water. 16, 17, 18, 18.02 grams of water over moles of water. And let's determine what those moles are. So how many moles, so yeah, please have your calculators out. We've got plenty of calculations today. So how many moles of ammonia do we have?
0.049.
So 0.049. And how many moles of water do we have? .94. All right, so we're going to now add both of those up because we need the total number of moles to get the mole fraction. All right, so what is it if we add both of those up?
6.989.
So we'll say 6.99. So this is our total number of moles. And to get the mole fraction, well, we know what the moles of that is, right? So to get our mole fraction is for ammonia is going to be 0.049 over the total number of moles, 6.99. And what does that equal? So what is our mole fraction for ammonia? It's going to be a relatively small number. Maybe to the -3.
7.01 times 10 to the -3.
7.01 times 10 to the -3. So this gives us our mole fraction. So these are what we're familiar with. And now we're going to determine what the molality is. So the molality is moles of solute over kilograms of solvent. Right? And I'm going to write that up here. So molality, moles of solute over kilograms of your solvent. All right. Well, do we know what the moles of solute is? Where's that at? Right there. So we're going to say molality is equal to 0.049. We have grams of this, but we need kilograms of this, right? So in order to convert that, right, you can do one of 3 things. You can actually put this into your calculator, this over 1,000, but this is going to equal 0.125. We just move the decimal over 3 places here. So this is moles of solute over 0.125 grams. So this is going to be our molality. So what is the molality of this solution?
.392.
So this is going to equal 0.392 molality, right? So we're not going to leave it in terms of moles per I'm sorry, this should be kilogram. We're not going to leave it in terms of mole per kilogram, is we're just going to actually, this will be our final answer, 0.392 molality. 0.392 molal, okay? All right. Calculate the mole fraction of a solute and solvent in a 3.0 molality solution of sodium chloride. So it seems here we're going to need to work backwards, right? Is here we have some molality. We're going to take this other value here. So let's take a look at that. So we have 3.0 molality. I'm going to convert this because we can't figure out what the mole fraction is until we understand what units are in molality. So I'm going to convert this into 3.0 moles of solute, which is the sodium chloride, over 1 kilogram. And you know what? This is going to be in 1 kilogram of water, so that's going to be our solvent there. Right. So 3.0 moles of solute over 1 kilogram of solvent, and our solvent is the water, and the moles here are going to be for sodium chloride, and we're looking for the mole fraction. All right. So 1 kilogram of water. So let's convert that into grams of water. How many grams of water do we have then?
1,000.
1,000. So we have 1,000 grams of water. Let's convert that into moles. So 18.02 grams per mole. So how many moles of water do we have?
55.5.
So 55.5 moles of water. And how many moles of sodium chloride do we have? 3, right? That's what it says, right? This is the information here. So we have 3.0 moles of sodium chloride. So in order to get our mole fraction, right, we need our mole fraction. So we need to do moles of our solute over the moles of the total. So which means we're going to have to add this up. This is going to come up to 58.5, and this is going to be our total number of moles. So now if we want the mole fraction for this, well, we're going to put this, our mole fraction is going to be 3.0 over 58.5. And this will equal our mole fraction. So what is our mole fraction there? 0.011. 0.011?
51?
Oh, 0.51?
Yes.
0.051. All right. This is our mole fraction of sodium chloride. What is the mole fraction? Just so we know here, what is the mole fraction of the water then?
55.5 over.
Yeah, so it would be 55, yeah, 55.5 over 58.5, right? And that should come out to like 0.95, you know, because all of this has to add up to just 1, right? So we can just do that there. If we just put 1 minus this, that would be the rest of the mole fraction for water. All right. The mole fraction, so here they're giving us the mole fraction. So still working with molality. We have mole fraction of iodine dissolved in some dichloromethane. So this is dissolved in the dichloromethane. Which one is the solute? Which one is the solvent?
The solvent's dichloromethane.
The solvent would be dichloromethane, and our solute is going to be iodine, and that mole fraction is 0.115. So here we're provided some information. We have the mole fraction of iodine. So the mole fraction of iodine is equal to 0.115. It's dissolved in dichloromethane. What is the molal concentration of iodine? All right, so we need the molal concentration of iodine. All right. We're going to make an assumption here. And the assumption we're going to make is that this is in a 1 kilogram solvent, right? A 1 kilogram solvent of dichloromethane, right? And the mole fraction here, right? Our mole fraction here is that we're going to consider this to be, we're going to consider this whole solution to just be 1 mole, right? And if we consider this to be in a 1 mole solution, right, then that means how many moles of iodine do we have then? I2. Right. If we just assume we have 1 mole here, then we're just going to assume that it's going to be 1 mole of iodine here. Let's keep on track here. They don't provide any density here for us. Is this not the one? No, that is not the one there. And we're to figure out, so we have a 1 kilogram solvent. So here, that means that our mole fraction for the dichloromethane so what's the mole fraction for our dichloromethane? It would be 1 minus this, right? So what is 1 minus this? .885, which we can also then make an assumption that we have, because we're considering just 1 mole, we have 0.885 moles of dichloromethane. Well, if this is how many moles we have, how can we convert moles into grams first? We can't, I don't want to convert it to kilograms just yet, but I do want to convert it to grams. And what would we use to convert that to grams? Right, periodic table. So the periodic table, we have carbon, 12.01. We have hydrogen, 1.01. And we have chlorine, that is 34.45. But we need to multiply that by 2. So what is the molar mass of dichloromethane?
81.92.
81.92. Is that what everybody else got? This is going to be 70. Oh, no, maybe it's a little bit higher because this comes out to be 70 itself. 70, 82, 83, maybe a little bit higher. Or is it 81? Could be 81.92. Just, can we verify that? 81. All right, so let's go. So 81.92 grams per mole, and then we're going to convert this into kilograms. So 1,000 grams, we have 1 kilogram. So how many kilograms of solvent do we have?
Maybe it's 82 because we have to multiply the H by 2.
Yes.
Because we have to do what?
Multiply by 2 for hydrogen.
Is it CH2? Oh, there it is, CH2. I missed that. There we go.
So it's 82 for
82.93. Thank you for catching that. All right. So 82.93. So how many kilograms of the solvent do we have?
.08192.
So then we're going to take 0.08192. So what is the molal concentration here? So 1.4 molal. All right. So again, we're just dealing with different ways on how to calculate molality, how to deal with these mole fractions for molality. The last thing we're going to introduce now is that we are able to use density in order to help figure some of this out. So here it says we have an intravenous infusion 0.556 molar aqueous solution of glucose. They've given us the density. As part of some postoperative recoveries, what is the molal concentration of the glucose? The molal concentration of our glucose. All right. So let's see what information. So I'm going to convert this here. So this is 0.556 molar. And I'm going to do I just want to change these units over, and we're going to go 0.556 moles of glucose per liter of solution. All right. Per liter of solution. Give me 1 second here. We have the density, so they've given us the density of glucose. Density of glucose, I just want to write this down. So we have 1.04 grams per milliliter. And this is now liters of solution, right? Is that this liter here is liters of the solvent plus the solute, right? This is equal to the solution. So in order to figure out the molality here, well, we need to determine how much of it is solvent, how much of it is solute, right? So we do have to separate that. And we can use part of this information here to convert these liters into grams. So we're going to have the grams of glucose. We can determine what the grams of water are here. And that's going to kind of be the direction that we're going to head for this. All right? So here we're assuming if it's 0.556 moles of glucose, moles per liter, how many liters are we assuming there are here? 1, right? So we're going to have 1 liter of solution, so 1.0 liters of solution. And we're going to use the density over here, right? So our density, we're going to convert this liter of solution into some mass here. So we're going to have density. And actually, it's not the density, it's the density, this is the density of the solution. I shouldn't put glucose there. I'm just going to put density, the density of the solution here. So we're going to use this. This is, let's convert liters into milliliters, and then we can use our density here. So this is going to be 1.04 grams over milliliters, and then we're going to convert this into kilograms. So there's 1,000 grams in 1 kilogram. And all of this cancels out really nicely. Watch this. So this cancels this cancels this. This 1,000 cancels this 1,000. This gram cancels this gram. So our answer is pretty straightforward here. It's 1.04 kilograms. Right? So 1.40 kilograms of solution. Well, if we know we have moles of glucose, well, let's figure out how many kilograms, because we have to separate that out of this. This here includes the solute and the solvent, right? So if we know the mass of the glucose, well, we can subtract it from the total solution, and that'll give us kilograms of solvent. So that's going to be our next step here. So we're going to take 0.556 moles of glucose. Glucose is C6H12O6. So let's determine what that is here. Is that we have, for carbon, we have 12.01 times 6. For hydrogen, 1.01 times 12. And for oxygen, 16.00 times 6. So this is going to be 72.06, 12.12, 16 times 6, 96?
Yeah.
Right. And then if we can just add all of that up together, what do we get? 180.18 grams of glucose for every mole of glucose. And let's do one more thing. You know what? Let's go one step further and let's get this into kilograms. So let's divide that. So here's our equation: grams over kilograms. So how many kilograms of glucose do we have? 1.04. Is that what we got?
Oh, sorry.
Okay.
Let's say you're asking about that.
No, this one up here. So take moles of glucose times the molar mass of glucose, divide that by 1,000.
I think I got 0.100. I don't know.
0.100?
Yeah.
Is that what we got? Okay. So now we can subtract that from the solution. So if we take that and minus 0.110 grams of glucose, let's say kilograms of glucose, whatever's left over is going to be kilograms of the solvent, right? The water that we're diluting this in. So how many kilograms of water or solvent do we have?
0.94.
What is that?
0.94.
0.94 kilograms of solvent. So now we can, since we converted those liters and we've separated out the solvent here, in order to calculate this, we're going to go 0.556 moles of glucose over 0.94 kilograms of the solvent. So what is our molality from that here?
.5, 0.59.
So 0.59 molal concentration. So here, looks like we're going to just do the reverse of that. So again, the only thing we've done this morning is we're just learning how to make these calculations that now include, mole fractions. We've included density. We've been able to calculate that. We've been able to calculate from molarity to molality, and now we're going to do molality to molarity. Right. So that will be the last one there. Let's see, let me erase this up here. These seem like some great extra credit questions that we're going over today. Man, wouldn't these be nice for some extra credit on the exam? I'm thinking, yeah. All right, so here, right, hint, hint, wink, wink, right? Today's lecture is filled with great calculations for extra credit. All right, anyways. We're going to start with this. So let me just write this information down here. So here we got 33.7, and I'm not going to use the M here. I'm just going to convert. We're going to say that this is moles of solute over kilograms of solvent, right? Because that's what that mole out, that little molality symbol here. Then we do have density. So the density of the solution is 1.35 grams per milliliter. All right, so we do have some information here. What is the molarity of this solution? All right, well, we have to get the mass of the solution, right? Because this is for the solution here. This is density of the solution. So what we need is the mass of the solvent and the mass of the solute, right? But the mass of the solvent we already have. What's the mass of the solvent? It's 1, yeah. So the mass of the solvent, yeah, this is simply equal to just 1 kilogram. Now we need the mass of the solute. So we're going to take 33.7 moles, and what is it we're using here? Nitric acid. So moles of nitric acid. And let's convert that into kilograms here. So we have hydrogen, which is 1.01, nitrogen, which is 14.01, and oxygen, which is 16. And we're going to multiply that by 3. So what is the molar mass of nitric acid?
63.02.
So 63.02, 63.02 for every mole. And then we're going to go 1,000 grams in 1 kilogram. This cancels this unit, this cancels this unit. We'll have kilograms of nitric acid. So how many kilograms of nitric acid do we have? So 2.12 kilograms of the solute, and we have 1 kilogram of that. So if we add those together, we get 3. Why can't I add? There we go, 3.12 kilograms. Right. So because we're going to use this, let's put this in here. So let's convert. We can convert this into grams or this into kilograms. Let's convert this number into grams here. So we're going to say 3.12 kilograms, and for every 1 kilogram we have 1,000 grams. Then we're going to use the density over here, and we're going to say for every we want 1.35 grams for every milliliter, and then because molarity Molarity is moles per liter. We're also going to make one last conversion here into liters. So we're going to say for every 1,000 milliliters, there's 1 liter. Let's cancel these units out. This cancels this. This 1,000 cancels this 1,000. This milliliter cancels this milliliter. This gram cancels this gram. So how many liters of solution do we have?
Point
0.231? All right, 0.231 liter. I think that's pretty reasonable. And so now to figure out the molarity, is that what we got, 0.231? Yes?
Yeah, I got 1.
I got
2.31.
Oh,
I got 2.31.
All right, so let's go. It looks like majority got 2.31. So in order to figure out the molarity here,
oh, I put 1,000.
we're good? Okay. So now we need moles of the solute, which we have. We're given those moles here. So we're going to put 33.7 divided by 2.31. This is going to be moles per liter. What is the molarity of this concentration?
What's your budget?
14.6 molar concentration. So all we've done for the last 45 minutes is we've just done dimensional analysis, including molarity, molality, mole fractions, right? Is that this is just some dimensional analysis in order to start using molality, right? So now let's talk about vapor pressure. Right, so we still have to cover vapor pressure, freezing point depression, boiling point. So as far as vapor pressure and how we can lower vapor pressure, right? In order to lower vapor pressure, is that we've had labs where we check the volatility of certain substances, right? This is how fast they evaporate or how slow they evaporate, and we put them on the thermometer and we measured that distance. So the more volatile something is, right, the faster it evaporates, right? So vapor pressure, right? Vapor pressure is very, very high. I'm sorry, vapor pressure is very low, and we seem to evaporate that very quickly. So there is a way to slow that. And I was hoping we have a picture of this, right? So we've talked about this liquid gas equilibrium in a contained cell where we do reach equilibrium at some point where we simultaneously go from liquid to gas in a closed system, and we reach some equilibrium. But this is, I think this is what we can look at here. I do have a picture on the next slide here. So when we put a solute into the solvent, right, is that the surface layer where we have our vapor pressure, at the surface, if I put a beaker of water here, at that surface, we have vapor pressure where the molecules on top, the water molecules on top, are slowly evaporating off. But if we put a solute into that, it reduces that surface area. So it's not just water molecules at the top. If I put a little bit of salt in there, well, now it's salt ions on that layer, and it reduces that surface area. So here, right, at this level here, we have just a bunch of water molecules, and there's a large surface area here, and this will then evaporate. But when we put some solute in there, right, the surface area is then limited. So this will actually slow down that.
The surface area, like the top or the?
This is where the surface area, it's right here.
Yeah.
So this is a light blue color, this is a gray color. So these up here, these are gas molecules of water, and this is our solution right here. So if you want to come up and just take a closer look at it, you can see it now. Yeah, so this is the surface area here, and now part of that surface area is taken up by the solutes, right? So it reduces that surface area so we can reduce just how fast it's going to, we're going to lower that vapor pressure, right? We'll lower that vapor pressure, and then we have less molecules of the solvent going into that gas phase. So now talking about the vapor pressures here, we use something we call Raoult's law, right? So Raoult's law has to do with partial pressure. So we did have a similar formula to this that we used in gases for partial pressure. And we can use that in order to determine partial pressures of solvents, partial pressures of solutions, right? So here is our vapor pressure of the solution, vapor pressure of the solvent, and then we have our mole fraction of the solvent. Right? So let's take a look at that and actually try and calculate something over here regarding that. All right. We need the new vapor pressure. So this is currently the vapor pressure of ethanol, and it looks like 92.1 grams of glycerin. I'm going to write some of this information as we're reading it. So I have 92.1 grams of glycerin. So 92.1 grams of glycerin. And we also have 184.4 grams of ethanol. So just first off, which one is a solute, which one is a solvent?
Bottom one solvent.
Solvent, right? Because this is the larger one. So solvent, this is our solute. And at 40 degrees, the pressure of just pure ethanol. So pure ethanol has a vapor pressure. This is vapor pressure of the solvent. The vapor pressure of the solvent is equal to 0.178 atmospheres. And it is asking us to compute the new vapor pressure. So we need the vapor pressure of the, I'm going to correct this here. I'm going to put solvent, not just SOL. So the vapor pressure of the solvent, what we need to determine is the vapor pressure of the solution. Well, in order to do that, we need to figure out what that mole fraction is. If we have the masses of these, we can determine what that mole fraction is. So let's first convert these into moles so we can determine what that mole fraction is. And then once we find that out, we just simply multiply by this, and it'll give us the new vapor pressure. So here, I wonder if I have these here so that we don't. Just for the sake of time here, this is 92.09 grams per mole of the glycerin, and ethanol is 46.06. So this is 46.06 grams per mole. So how many moles of glycerin do we have? And how many moles of ethanol do we have?
For the top one, 1.0.
Moles of glycerin, okay. And moles of ethanol.
4.0.
What is it? 4.0 moles of ethanol. So what's the total amount of moles that we have? 5. So the total amount of moles we have, if we want to figure out what the moles of the solvent is, so moles of the solvent, 4 divided by the total number of moles, 5. 4 divided by 5 is 0.8, right? So this is our mole fraction. It's simply just 0.8. So now, in order to figure this out, we're going to take that mole fraction and we're going to multiply it by that pressure. So we're going to get 0.80 times 0.178. And what is the new vapor? Because now we're lowering that vapor pressure, right? When we lower the vapor pressure, right, we're making it less likely to evaporate. I think I might have reversed that saying a little while ago. Hopefully I didn't. But yeah, a decrease in vapor pressure, right? So what's our new vapor pressure of the solution? 0.142 is our new vapor pressure, right? So here is our new vapor pressure. All right. Now in order to understand what we consider boiling point elevation, freezing point depression, again, these are colligative properties of these solutions. So a solution will boil higher. And these two we really need to, I have another figure that I want us to look at. Hopefully we're not too far off from that. But in order to change the boiling point of a solution, or of some solvent, we add a solute to it, and it changes that boiling point. But when we do that, right, we actually increase the boiling point temperature. So by adding a solute into the solvent, we raise the boiling point temperature. And when freezing, this is what we experienced in the lab, is that when we add a solute to it, we lower that freezing point temperature. Right? So when we add it, we raise the boiling point temperature or we decrease that freezing point temperature. But both temperatures are positive quantities, right? Well, the temperature change anyway, right? So by changing that, let's see if we can, there should be an image here. Let's take a, there it is, there's the image I'm looking for. So here we see this phase diagram, and we can see when it converts to gas, when it converts to solid here. Temperature's decreasing, temperature's increasing, right? Pressure is increasing, pressure's decreasing. But if we're at some constant pressure, right, here is our solvent. And as we add a solute to it, it decreases that temperature that it needs to freeze. And we can see going from liquid to gas, right, is that we're going to increase that boiling point solution. So here, right, we take that, we put a solute in there, and now for the solution, we've now increased that boiling point temperature. So this is the one we worked with in the lab, right? So this doesn't stand for final, right? This is the changing point temperature, the freezing point. This is molality, and this is our freezing point depression constant. And this is our our boiling point elevation constant that we have here, right? So when we use these, we just kind of have to be a little cautious when we use those. We're going to make some calculations introducing those, and we see that these values are different here, right? Is that my boiling point elevation constant is different than my freezing point temperature constant, right? We have boiling points here, freezing points here. And when we're calculating these, I'll make a note of it when we actually get to those calculations, right? So here we're going to assume our ideal solution, let's see, where the boiling point is what is the boiling point of a 0.33 molar solution of non-volatile solute in benzene. All right, so let's look at benzene, and we're looking at boiling point. So the boiling point of benzene. So we're going to go over to this table here. Hopefully benzene is there. Yes, benzene is there. And what is the boiling point of benzene?
80.1.
80.1 degrees Celsius. Now, our formula for this. Our formula for this is the change in the boiling point temperature is equal to molality times this K sub B, this freezing point constant. So we have the molality, and we have this boiling point, the boiling point constant we did not write down, but let's get it real quick. For benzene is 2.53. So K sub B is equal to 2.53 degrees Celsius per molal. I think in the lab we did yesterday, these are the same. So when you see degrees Celsius per molal, this is equal to degrees Celsius kilograms per mole, right? That these two are equal to each other here. But now that we know those values, right? 0.33 times 2.53, and this is going to be, let me get these units correct here so we can cancel them out. Okay, this cancels this. So what is our temperature change here? So we'll just go with 0 point. So this is the temperature change of the boiling point. If this is the boiling point, 80.1 degrees Celsius, this is something that you need to remember, is that this is only the change to the boiling point. But with what we've discussed, and looking at this phase diagram and what happens when we to the boiling point when we put in a solute, do we add this or do we subtract this change? We're adding to it because this is boiling point elevation, right? Is that what we increase the boiling point when we add in a solution. So we're going to add 0.83 degrees Celsius to that, right? So now we are at 80.93 degrees Celsius is the new boiling point, right? So we are increasing that boiling point there. What's the boiling point? So they've given us some other information now. A couple more to deal with here. We do have one for freezing point. Let's look at the freezing point one before we do this other one here for boiling point. So we'll do the freezing point one real quick. And we are using nitrobenzene. I don't think nitrobenzene was on this list. There it is. Nitrobenzene is on this list. So our K sub F, as we're looking at freezing point, K sub F for nitrobenzene is 8.1. And for nitrobenzene, we'll do the freezing point is 5.67 degrees Celsius. Did they give us the concentration? 1.85 molality, so 1.85 molality. So if we set this up here, the freezing point temperature change, right? It should change by taking 1.85 molal times that by, and this is degrees Celsius per molal, 8.1 degrees Celsius per molal. This cancels this unit. So what is our change in freezing point temperature?
14.9.
So you said 14.98? 14.98. We'll just round that to 15. So 15 degrees Celsius. This is freezing point temperature. Right? When we add a solute and make a solution here, what happens to the freezing point temperature? It decreases. So are we going to add it or are we going to subtract it to this? Right, we're going to subtract it. So we're going to go minus 15 degrees Celsius. So what's the new freezing point temperature now? So negative 9.33 degrees Celsius is our new freezing point. So we just have to remember that when we're dealing with boiling point, freezing point, and those changes, whether we added or whether we subtracted, is that we do have to remember that, right? If we're dealing with boiling point elevation, is that we're going to add it to that temperature. Freezing point, we're going to subtract it from that temperature. Let's take a look at this other one here. Let's see what information we're given. So this is going to be a lot more detailed because we don't have the molality here. So we're going to have to calculate molality in order to get to this one here. So boiling point glycerin, so glycerin boiling point, do they provide that for us? Is glycerin in there? But what do we have? Let's look at the other information that we have here. Okay, well, it's 1 gram inside of 47.8 grams of water. Right? So we have 1.0 grams of glycerin. And we have 47.8 grams of water. All right. So as far as boiling point goes here, this is our solvent. Right? And water boils at what temperature? 100 degrees, right? So we know the boiling point. So the boiling point of water is equal to 100 degrees Celsius. And then we're going to introduce the solute, and then we're going to change this. Right? But we do need to get that molality concentration here. So we need moles of solute. Moles of solute over some kilograms. So here, so let's convert this. This one's pretty easy here. So let's convert this one first. Is that first we're doing grams into kilograms, so that there's 1,000 grams in 1 kilogram. So how many kilograms of solvent do we have? So here's our kilograms of solvent. And now we just need moles of glycerin. And what was the, did we calculate that? What is the moles? Oh, I think I have it here, 92.09. Saved it. All right. 92.09 grams per mole of glycerin. Is that right? Let's just want to make sure you're 92.09. All right. So how many moles of glycerin do we have? .011. All right, so this is how many moles of our solute we have. So now, that's going to be our molality. So we're going to get 0.011 divided by 0.0478 This is moles over kilograms. So that's our molality. And now I don't believe we have the, let me get that information for you because I don't believe we have it. This boiling point is going to be 0.512 degrees Celsius per molality. I had to look that one up, yeah. So we know what that one is. So this is given to you. You don't have to calculate that, but we're going to go 0.512 degrees Celsius per molality. So this molality cancels out that molality. So what's our temperature change there?
I think it's 0.116.
0.116, I think that's a good value. So here we're just going to add 0.116, so we're going to add 100.12, we'll just round it, 0.12 degrees Celsius. Oh, there we go. So this would be the new boiling point after we add that in. All right. Couple more problems to deal with. I think I'm going to just backtrack here and just look at, just so we get the idea of distillation here. When we distill something, for those of you that are moving into biology majors, chemistry majors, chemical engineering, is that once you get into organic chemistry revolves around a lot of purification, right? A lot of distillation. So a lot of this happens in organic chemistry. So how we distill this, right? How we purify some solution that we've made, right? Is that we're going to heat this to boiling, right? And whatever the solid is not going to evaporate out, right? The solid is going to remain down here. But the solvent, if you want to purify that solvent, that's going to evaporate here. And this is water. This is water. So cold water comes in here, and it cycles around, right? But once the vapor of the solvent comes to this point here, it's cooled down by this tube here. And it collects that vapor, it collects that solvent here, and we get some purified solvent now, so that we can remove that solute, all those solute particles, and purify that solvent. So, but a lot of that happens in organic chemistry there, right? So, boiling point, freezing point, right, is that this is the reason why rock salt is used. They use it on the highways. They use it anywhere it snows. By adding salt, we lower that freezing point of snow, of water, right? So it will melt just because it's simply not cold. It has to get a little colder in order for it to freeze. So we use that. They use it in commercial airlines here, right? Spraying some solution here to lower the freezing point of the ice that's there, of that water. So that it'll melt relatively easy. So here we have what we can consider semi-permeable membranes. Right? Semi-permeable membranes. So between some solvent and solute, semi-permeable membranes only allow the solvent to pass through. Right? No solute particles, right? Especially with water. So if we put some membrane up, wish we had, let me see if we can get to a picture of this. Right? So here in this container here, this is what we consider a semi-permeable membrane. Right? And over here we have some solvent, and then here's the solution of solute particles and the solvent. Now the only thing that can pass through here is simply just the solvent. As though those molecules are small enough to pass through the membrane here, right? The solute particles are just too big, and they will not pass through that semi-permeable membrane. So here we have what we consider different concentrations, right? Is that here this is highly concentrated right? Because there's some solute particles here, and this has no concentration. This is pure solvent, right? So as far as the concentration of the solute concentration is much higher here than here. So what has to happen is we have to have some balance, some equilibrium, in order to maintain two consistent concentrations. So what happens here is that water passes through here to dilute this end, right? And the water level will lower, and then we dilute this end. But when we do that, we see that level there a little uneven. This builds up a back pressure, right? That back pressure is what we call osmotic pressure. And we can measure that. We can actually calculate what that pressure is. We can reverse this. You ever heard of reverse osmosis, right? So reverse osmosis would be, we need to apply a pressure greater than that osmotic pressure, right? This back pressure here that we see there, right? That osmotic pressure, if we apply a pressure that's greater than that, then we can reverse this and we get the solution here, right? Reverse osmosis is supposed to make our water, right? Makes your water a lot more filtered out, right? Well, the reason why is if we reverse this through that membrane, the solute particles can't pass, and the only thing we get is just a solvent, which would be water in most cases of reverse osmosis. Is that we apply that back pressure, we use this membrane, and it clears out these solute particles so that we just get some purified water there using reverse osmosis. Now, as far as calculating they call it osmolarity, osmotic pressure, osmolarity. So to calculate osmotic pressure, is that this is our symbol here, right? It looks like a little pi symbol. That's going to be our osmotic pressure. So our osmotic pressure is calculated by using molarity, some rate constant, and then some temperature, right? Temperature in Kelvin. Our rate constant we're familiar with, 0.08206 liter atmospheres per mole Kelvin, right? And then here, right, this is in moles per liter, so we can see how the moles and the liter is going to cancel out, Kelvin cancel out, so our osmotic pressure is going to be read in atmospheres. So let's take a look here. Assuming an ideal solution, what's the osmotic pressure of a 3 mole solution? So what is our osmotic pressure of a 0.30 molar solution? We know what the rate constant is, 0.08206 liter atmospheres per mole Kelvin, times some temperature in Kelvin, 273.15 plus 37 degrees Celsius. So, not a bad calculation. As long as we know how to set that up, right? We should be able to set that up. And what is our osmotic pressure there? So 7.64 atmospheres, right? So when you're just given everything, all the values there, we just set it up and it's just a very simple calculation. The next one does require a bit more here because we're not given the molarity. What we're given is 5.0 grams of methanol, even better, CH3OH. And that is going to be in a 0.75 liter solution. So what we have to do here is we have to convert these grams into simply just some moles here. So let's see what we have here. We have carbon, 12.01. There's 3 hydrogens, so that's going to be 3.03. And then we have oxygen, which is 16.00, 4, 0, 11, 31.04. So 31.04 grams per mole. That cancels this gram and this grams out. So now we know what the molarity is. So let's do 5 divide by 0.75 divide by 0.31. And what's our molarity there?
.215.
All right, so we have 0.215 molar. We're going to multiply at 0.08206. We're going to multiply that. Did they give us the temperature? 37 degrees, so still 273.15 plus 37. So what is our osmotic pressure? Osmotic pressure?
It is 4.17.
Right. So there we have some osmotic pressure. All right, so just about 10 minutes left. I think we can finish this off here. So as far as semi-permeable membranes, a little bit of biology here is that the middle one here, let's start with that one. The middle one here is what we consider an isotonic solution. Right? Isotonic solution is that when we have some red blood cell, I'm going to use green here, right, is we have some, these red blood cells can act as some semi-permeable membrane, is that water can enter this and water can also leave that. So if we have some concentration, let me use black. Okay. So when the concentration, and let me put some solute particles out here, right? When the concentration of water is equal, when these two are equal to each other, let me put some water particles in here. Right? So here, we can see that the concentrations are pretty equal, right? Any water that passes through is the same amount of water that's going to go out, right? There's no net gain, there's no net loss of any water in an isotonic solution. But in what we can consider to be a hypotonic solution, in a hypotonic solution, there's a high amount of solutes inside this red blood cell. So what happens is we're going to get a bunch of water that's going to try and dilute this. But not very much water is going to be leaving that. So what this happens is this engorges the red blood cell. And this is what we're going to call hypotonic. This is isotonic. So hypotonic, isotonic solution, and then something that we call a hypertonic solution. So this is hypertonic solution. And we see that the solute particle is a lot here. So what happens is water has to leave this blood cell, and not much water is going to go into there. So we kind of have the opposite. So as this one is going to increase, it's going to actually rupture the red blood cell and kill it off. As here we have the opposite effect in a hypertonic solution, where these red blood cells are going to end up shrinking versus engorging. And then that brings us to our Van Hoff factor, which I think I have enough time to explain here. All right, so this Van Hoff factor is a ratio of solute particles in some formula, and how we determine that I value. So we're going to put this, the simple part of this is that I is equal to the number of ions if there are no ions, I is equal to just the number 1. So if we take a look at sodium chloride, if we put sodium chloride into water, I get sodium plus I get some chloride. So our Van Hoff factor I here for sodium is going to be, how many ions do you see here? 1 ion here, 1 ion here. So how many ions? 2. So I would equal 2. And if we did, let me erase some of this up here. Let's do calcium chloride. If I put calcium chloride into water, we're going to get some calcium, 2 plus we're going to get 2 chloride ions. So here, how many ions do we see? 3, right? There's 1 here, there's 2 here, is that I is going to equal 3. What would I equal for aluminum fluoride? When we put this into water, what happens? We get aluminum plus 3. So what was our I going to be? Yeah, I is equal to 4. Now, if I put this, C12, H22, O11. So this brings back the idea of electrolytes and non-electrolytes. So what would our I factor be here? Are we going to create any ions here? No. So I would then equal simply just 1. And then let's take a look at some, how about, all right, calcium sulfate, right? What's the charge on sulfate? Minus, this is 2 plus. So when this ionizes, we're going to get calcium plus we're going to get some sulfite. So how many ions are we going to get here? 2. But if I change this, what if we did this? How many ions am I going to get here? 5. We're going to get 2 phosphate ions, 3 calcium ions, is that I would equal 5. And then just this last bit here, just a couple minutes to go over this topic. So just kind of identifying these colligative, these solutions here, right? Is that here, the salt water here is considered to be homogeneous, right? Because we can clearly see through this water here. Even though this may look homogeneous, like we can't really look through it, is that here, this is what we're going to consider a colloid. Because there are some particles in the milk, but the particles are suspended. Even if you left your milk sitting in the fridge for a week, right, those particles don't separate, right? Those are colloid particles there. Right? And then this is just mud. Mud is just simply some heterogeneous mixture here, a bunch of rock, dirt, sand, clay, and you can clearly feel the grit on that. But we can't see it for this. So there are some other examples we can see, even here in these, right, is that there's small particles here, but when we shine the light on them, right, this is a colloid, right, solution, is that we can see now, reflecting some light on that, was that we can actually see some of those particles. So then just some examples here of different colloid systems here, right? Smoke, dust, right? Or some other ones here. Yeah, right, clouds, frost, like milk, mayonnaise, butter, right? Is that those particles don't settle at the bottom of those. And then I think our last topic here is just emulsion and emulsifying agent. I got like 20 seconds here. So this is how we wash our clothes, right? Is that this is soap. Soap has an ionic end, and then it has this nonpolar tail. And we know that like dissolves like, So here, stuff like oil, if you get oil in your shirt and we use some detergent here, well, the oil, which is non-polar, is attracted to the inner portion here. Right? So as it's attracted to the inner portion, water, which is polar, is attracted to this polar outside, and it will just carry that dirt away from us, right? But some definitions you do need to know is emulsion and emulsifying agent. And the emulsifying agent is what kind of keeps this together, right? Is that how do we make mayonnaise? We simply just whip up some egg, put in some salt in there, and we can make mayonnaise because when we mix that, like the salt is kind of acting like an emulsifying agent in order to keep that system together, those particles together, versus just having them sink. But please be familiar with emulsion and emulsifying agent. And we have now finished our last chapter. Exams starting tomorrow, our lab exam. Make sure you bring your lab manual, right? Make sure you bring your lab manual, your lab notebook. Anything from lab 4 to lab 22 is fair game. So as long as you can read it and understand your calculations, again, the lab exam isn't going to be terribly difficult, and it is multiple choice. No, it's just a paper exam. But for 202, yes. For 202, the lab final